Okay, this is the third part of our chapter about firms theory, and this is about cost minimization, right? And so cost minimization, the way you have to understand it is basically that is an alternate theory of the behavior of firms. So imagine you have a firm with increasing returns, right? So you cannot really maximize profits. So what can you do? What is a more basic theory of behavior that is not as demanding as profit maximization, right? Another example of profit maximization failing is when you have a firm that is, for instance, owned by the government. So if you have an electricity distribution firm or electricity generation firm that is controlled by the government, it's not necessary for them to maximize profits, right? For instance, they may have different goals, like they may have to have a certain target of quantity of electricity generated, and then what they really do is minimize cost. Okay, so cost minimization covers these cases, and basically is that, in fact, it's a necessary condition for profit maximization, but it's not sufficient, right? And what we want to do is that we want to find what are the minimal costs possible to produce a fixed level of output. And then this problem, for simplicity, is going to be studied in terms of a single output. But it turns out that you can actually do it for a general problem later, right? So, as I said, sometimes you don't want to do profit maximization. Yet another reason is that firms are not price takers in terms of outputs. As I said, there are increasing returns to scale, and then you have this profit maximization is going to go to infinity. You don't want to do that. So instead, we just study the cost minimization problem. So the cost minimization problem for the case of one output is basically minimize the cost, which is the multiplication of the cost of inputs, or W, which is the price of each input, times the quantity of inputs. Here we know that our convention is that Z is a positive quantity. And then subject such that the production function evaluated at the input level is greater than or equal than Q. So remember that in our notation, the production function is evaluated at the positive quantity of inputs, and then this will tell you the production possibility frontiers. And you're telling me that I want to find the minimal cost that produces at least a quantity Q. So this is exactly the same problem as the expenditure minimization problem in the consumer case. Replace the Q by the utility level, replace the utility function by the production function F, and then instead of finding the commodity bundle X here, you have the inputs bundle, which is the Z, and then you have prices, and here is W, so it's the same problem. Okay, so the optimized value, the solution to this problem is what is called the cost function. This is exactly the same object as the expenditure, which was a function of prices and of the utility level. So here instead is a function of the prices of inputs W and of the output level Q. Now the optimizing set basically is this demand function, which is set of the prices of inputs and the Q level. And this is called the conditional factor demand correspondence. So it's the demand for factors or inputs, okay? Now, the produce level is going to be assumed to, as always, by definition, a positive quantity. It's going to be assumed strictly positive and is fixed. For all this chapter, Q is fixed. Now, first order conditions allowing for corner solutions are known at this stage. So just derive this problem with respect to the Lagrangian, and then I have WL, which is the price of the input, greater than or equal than lambda, the Lagrange multiplier, with the partial of the production function with respect to the input ZL, and equality holds whenever this is positive, right? So equality, as I said, holds here whenever the quantities are positive. And then in matrix notation, we can write it in the Karush-Kontaker form. The vector of inputs is greater than or equal than lambda scalar with the gradient of the production function, and then the complementarity conditions that tells you that this bracket is 0 whenever Z is positive. Otherwise, the inequality can hold. And you also have the interpretation for the lambda, which is the marginal cost of production. Okay. Now, what are the properties of this cost function? Turns out that they're the same properties as for the expenditure function that you learned in the previous chapter 3 in the consumer part. So the properties of this function that is a function of W and Q, fixed Q. And now C is a homogeneous of degree 1 in the prices of inputs, that are non-decreasing in Q. So first you first Q, and then you see that is homogeneous of degree 1 in terms of prices of input. So the answer is very simple. It's just minimizing a linear function with respect to this reduction function constraint. So because the objective is linear in W, that's the only time W enters a problem, then obviously it's going to be homogeneous of degree 1 because of the linearity. You just multiply W times the quantity of inputs, you multiply alpha, being a positive scale, times the input prices, and then you get yourself alpha of cost, okay? Now, C is a concave function, so we already proved concavity for the expenditure function in the consumer chapter, so this is already understood. It's the same problem mathematically, so we know C is concave on prices, W. And now, right, we have also use of convexity. So it turns out that if the production function has non-increasing returns, then the production set, in fact, is convex again. So for a fixed Q, then this set of the input set such that Q is a feasible output level at the levels of F set, the production capacity of production. Then if this set is convex, right, then you have basically that you can characterize the following conditional production set. It's conditional on Q. So actually I will write it like this, with a Q here, because a Q is fixed, and now by fixing Q, turns out that I can use the cost function conditional on Q as the support function of this convex set. So it's the same idea as before. I use my hyperplanes, or basically lines of W, which are prices, and then I evaluate a candidate set input, and then I check these inequalities for the cost function. So I fix the Q, and then I check for a fixed price W, whether the multiplication of the prices times the candidate set is greater than equal now than the cost. This is the complete opposite to the profit case, because costs are minimal. So any other quantity that is not the cost minimization quantity has to be slightly above the cost function, because the cost is the minimal quantity, right? And now you have to do it for all W. Okay, so this is exactly the same problem as before. And again, I show you in my board here. Now the problem will be slightly different, because you have this problem of the isoquants. So you have here input 1, input 2, and then you're gonna have things that look a lot similar to the indifference curves. So these are gonna give you level Q1, level Q2, right? And then basically the convex set that we're talking about is this set here, okay? Now, how do I recover this set? Well, I'm gonna cost minimize. So remember, this is basically the problem of the expenditure minimization problem. So this is a minimization point, this is a minimization point, and this is yet another one. If I change all prices, eventually I'm going to recover this set, right? And so on. Okay, so that's what this is. It's very easy. And now it's just following the expenditure function. And now remember that we have this envelope theorem application for the profits and for the expenditure function. Here is the same. It's called the Shepard's lemma, and basically tells you that the demand of inputs or factors, whenever it's a function and it's differentiable, then it's actually just the gradient of the cost. Remember, Q here is fixed, so you're just deriving with respect to prices, W. And then if this supply, sorry, this is part of the supply, of course, but it's called usually the demand of factors, but it's part of the supply. And then if this is differentiable at prices, then turns out that this matrix of substitution with respect to the prices W is equal to the Hessian of this cost function. So remember, the cost function here is concave, so therefore it has to be continuous. So continuous, the continuous property gives you symmetry of this matrix, and also it gives you the concavity gives you negative semi-definiteness. So this is the same as the case of the cost. And then here finally have the singularity in prices. And now finally, if f is concave, that means basically you have a non-increasing returns to scale, and C, the cause is that basically C is a convex function of Q. And in particular, marginal costs are non-decreasing in Q. Okay. Now, the proof of these properties are very similar to the case of the expenditure case, so we're going to skip it. And now notice that sometimes it's useful to know this. You can, in order to solve the profit maximization problem, sometimes this is hard to do. So a way to simplify that problem is to solve first the cost minimization problem. Whenever firms are profit maximizing, remember, these two things may not happen at the same time, but if we assume profit maximization and you want to solve the profit maximization problem, a trick you can use is first minimize cost and then obtain the cost function. Now the cost function is conditional on the quantity Q and is a function of prices W. So then you replace it back on the profit maximization problem, and now this problem becomes an unconstrained problem, which is simpler to solve, which basically tells you maximize the output, which is the only variable of choice now, conditional on the price vector output prices P and input prices W. So now the necessary conditions for this is basically that prices are equal in the interior case solutions to the marginal cost. So this is basically the famous equation in econ. Marginal income, right? Marginal revenue is equal to marginal cost. And then again, because we have corner solutions, we allow for an inequality. It is an equality whenever you have non-corner solutions, positive quantities. Okay? So we're going to conclude this chapter with a note on aggregation of firms. So I asked you to go over the chapter of aggregation of demand. We usually have negative results there. In contrast, in aggregation in firms, results are very simple and easy. All of the simplicity comes from the fact that firms are assumed to be profit maximizers, which is a very strong assumption of behavior, and also they happen to be price takers. So together, these two assumptions makes aggregation extremely easy. So let me tell you what I mean by that. So what is the aggregation problem? Suppose there are capital J production units. So for instance, imagine there are 2 production units. And each production cell of each firm is denoted as capital YJ. So here in my example, I have Y1 and Y2. I'm going to assume they are not empty, closed, and satisfy free disposal. So remember, free disposals, I can get rid of my inputs for free. The individual profit function and supply functions associated to each of these firms are pi of J of prices and Y of J of prices. So how do I define aggregate supply? Well, aggregate supply is the summation of these supply functions. So we're assuming now functions instead of correspondence, just for simplicity. And so notice that aggregate supply is just the sum of individual supplies. Now, let's characterize the properties of this aggregate supply, right? So what I'm going to tell you is that this aggregate supply will have the property that it can be generated by maximizing profits subject to the joint production process. That means if I take Y1 and Y2, the production sets, merge them into a single firm, right? And then I maximize profits there, and then I produce the aggregate supply. This aggregate supply is going to be exactly equal to the summation of the individual supplies that comes from individual profit maximization. So what I'm telling you is that in the case of firms, there is an equivalence of the centralized problem of every firm in isolation maximizing profits, and the centralized problem, which means that I basically nationalize, take all the firms and put them together and then maximize profits there, they produce the same aggregate output, okay? So basically, the substitution matrix of this supply vector is going to be symmetric and positive semi-definite, as you can notice, because if I apply the derivative operator here, it enters the summation, and this is a summation, so this derivative of the aggregate supply is equal to the summation of these individual substitution matrices, which each of them is positive semi-definite and also symmetric. So summation of symmetric matrices that are positive semi-definite is also a symmetric and positive semi-definite matrix. So let's define now what is this aggregate production set, which is the basis of the centralized problem. So this is summation of sets. So it's a new thing. So notice the definition. So the summation of sets is the set of production plans such that for any production plan in the aggregate production set, I can basically take the collection of J firms and produce their sub-production plans such that when added up, I get back my aggregate production set, okay? So let now the pi star of prices, which is the profit of the aggregate production set. So maximize this aggregate production set, and I obtain this aggregate production, the aggregate profit function by a star. And then the maximizer, which is the aggregate supplies of this centralized problem. In this imaginary problem where I am using the whole collection of firms and then merge them into a single firm, centralized problem, I obtain the supply y star. So now notice the following result, which seems deceptively simple. It tells you that for all positive prices, we have the following equivalence. We have here that on the left-hand side, that the profits are in the centralized problem are equal to the summation of the decentralized profits function. So that means that if I let the firms individually maximize profits under price taking and I aggregate their profits, this is the same profit level that if I maximize directly under price taking the centralized problem where I am actually dealing with a joint production set, capital Y, okay? And then the second part, which is actually a direct consequence of the previous one, is that the supply function in the aggregate supply function, which is the maximizer of the centralized problem, is equal to the summation of the individual supplies. The individual supplies is the result of maximizing profits at the decentralized level. So this basically gives you an equivalence between the aggregate problem or centralized problem and the decentralized problem. Now let's prove it. So for the first equality, notice that if we take any feasible plan in the individual production sets, then it turns out that I look at my aggregate profit function, and because it's maximal, it has to be greater than equal that the prices multiplied by the summation of any other production plan, in particular the summation of J production plans. Now, because this is the maximum, it then means that this aggregate production, aggregate profit function, sorry, is greater than equal than the summation of the multiplication of prices times the individual supplies. But basically this means that this profit here is greater than equal than the summation of profit. So we have proven one part of the equality, right? Now we have to show that the reverse weak inequality holds, therefore proving equality and therefore proving item number one. So now for the second part, consider any production plan Y that is feasible in the aggregate. Then I know by definition that P times Y is equal to P times parentheses the summation of Yj sets, which are the centralized productions in each firm, because that's the definition of this aggregate set. And I know by profit maximization that this summation of inner products is less than equal than the individual summation of individual profit functions. So that means that together it has to be remembered that this object here was whole for the profit, aggregate profit. So this implies that aggregate profit is less than equal than the summation of profit. So together, 1 and 2 gives you the first item. Now, just by applying the Houghton's lemma, by differentiating these two sides, I obtain the implication number 2. Okay? So this result implies that we can decentralize the aggregate firm profit maximization problem into maximizing the profits of each firm separately. Okay, that's pretty cool. So efficiency, we have a definition of efficiency. So a production vector y is efficient if there is no other y prime such that y prime is entry by entry greater than or equal to the original y, and such that this y prime is different from y. Okay, so at least there is one entry where they differ. So therefore, at least there is one entry in which y prime is higher in terms of outputs, basically, because this is positivity of outputs. So an efficient plant has to be on the boundary, but not all boundary points are efficient. So obviously, if I have an efficient point, I cannot improve. So it has to be the boundary of the production set, okay? So now, proposition. So if a small y is in capital Y, so production plan is feasible, is profit maximizing for some positive price? Turns out y is efficient. So if you're profit maximizing, you're going to be efficient. So is this something sensible? Yeah, we're going to prove it. Suppose otherwise, towards contradiction, there is a y prime such that y is different from y prime and y prime is greater than or equal than y. So contradicting the definition of efficiency. By positive prices, this means that if I multiply this price times y prime, then because there is one entry which is strictly greater than the other and prices are strictly positive, it has to be that this inequality holds strictly such that P inner product with y is strictly smaller than P times y prime. But that means that y cannot be profit maximizing, because if it is profit maximizing, then it cannot be below, right? It's below the point in the that is feasible and gives you a higher profit. So basically, if you are profit maximizing, then the entries and the supply correspondence have to be efficient points. So this is very important because this is telling you that firms left to their own devices, so looking for profit, being greedy, they reach something that is really cool, which is efficiency. They are not wasting anything. Okay? Now, so no waste. This is the key of this. If a collection of firms, capital J, independently maximize profits for a given price common to everyone, which is strictly positive, then turns out that the aggregate production is socially efficient. So that means if I right now nationalize possible firms, you are still price taking, and then you maximize in the centralized way this problem. This is exactly the same if I left their firms maximize profit given conditional on prices. And if they do it independently without the centralized system, they will still reach efficiency in the social sense. So there is no waste at the level of this social level. So suppose that so this is a corollary of the previous part and of the previous theorem of the equivalence. So we said, and now this is called basically the first welfare theorem. So it means that if I let firms to be completely decentralized, then under the conditions here by profit maximization, the joint production is socially efficient, even if their objectives are individual. And if they're maximizing individually profits without coordination, they reach social efficiency, which means no waste at the social level. Okay? And again, here we're assuming a lot of things. We're assuming price taking, we're assuming perfect information, so no inattention to prices. And basically, but the main assumption here is basically that firms are profit maximizing. Okay? If firms are not maximizing profit, then this will not happen, right? Again, we have versus government firms that may not be looking to maximize profits, right? Now suppose that y is convex, so remember non-increasing returns, then every efficient production plan y in capital Y is profit maximizing production for some non-zero price vector. So this is called the second fundamental welfare theorem. So basically this tells you that you can actually do a social engineering design here. So you have a production set that is the aggregate production set. And I don't want to nationalize production. I want to let firms do their own thing because I don't want to put bureaucracy here. So what I'm going to do is I'm going to let each firm individually maximize profits, but still deliver the level of this efficient outcome at the social level. Why I want it to be produced, okay? So then what I'm telling you is that the government can fix a particular price, basically give you a coordination device. I'm gonna tell you a price and you will take it as prior. You will be a price taker of this price given by the government. And when you maximize according to that price, you will individually produce different production plans that when added up will give me any point in the efficient frontier. So as the government, I can pick a point in the efficient frontier that I like, and then fix a price, and then tell you maximize profits, and then you will deliver to me this aggregate production plan that I desire. Caveat, I'm gonna need that prices for some goods may be zero, okay? But this is not market prices, so I can do it because I'm the government, okay? So the proof is actually very cool and uses a mathematical technique called separating hyperplane theorem and uses heavily convexity, okay? So before going there, I'm going to show you graphically what we're gonna do. So you can see in my diagram what I mean by the separating hyperplane theorem. So the separating hyperplane theorem claims that if you have two convex sets that are close, and of course mainly they are convex, you can always pass a line between them that separates them completely, okay? Especially, you can separate them completely because they are disjoint. Now, let's go to the second figure that looks like a Pac-Man, right? So can you pass a line that separates this convex set, the small circle here, from the Pac-Man? You cannot, right? There is no line that separates them. So now, what is the idea? So here, we're going to have our production set, and above, we're going to have basically we have the profit maximization problem. So we want to pass a line, which basically are prices that are going to separate these production sets from the objective of the firm. And this will give you a particular point in the production set, okay? So now let's prove it mathematically. So suppose I have a point that is efficient. So I already defined efficiency. And now I'm going to define the following set, which is the first convex set I need. So this set is indexed by this production plan and is called capital PY. And this is kind of an upper contour set according to the order of vectors. So these are all the Y primes production plans such that the production plans are strictly whether entry by entry are greater than Y, okay? So this just means that entry by entry, they have more quantity of everything. Remember that we have negative entries are inputs. So these guys having a greater entry of a negative quantity means they use less inputs, okay? And for outputs, they actually have more quantity. So the set Py is convex. So how do I know it's convex? Take two Y primes, take a convex combination. This convex combination is still going to be above Y, so it's convex. And given that Y is efficient, it has to be that if I take basically this set or upper contour set strictly and open, with the intersection with Y is empty, right? Because there cannot be a point that is better in every entry if the points that I'm fixing Y is efficient by definition of efficiency. Now we can invoke this theorem I mentioned you. You can check in the appendix of mathematical appendix of Mas-Colell, that is called the separating hyperplane theorem. Okay, that basically needs needs three components. So I need two convex sets. I need that the two convex sets have an empty intersection, right? And if that happens, we're in this world, and then I can pass a line, which is the price that separates them. Okay, and this established that there is some vector that is different from zero, such that if I multiply this vector times y prime is greater than equal than pi, sorry, of prices times, these are still not prices, by the way. This is just a vector because we haven't established they are non-negative. But now they are a vector, and the inner product of y prime in this set py is greater than equal than the points w prime in the production set. So basically, you have this line, and if you multiply this with the vector here, this is going to give you a lower quantity than the multiplication of this vector with a point here that is above. Now, the final part is basically that I have to show that, in particular, this implies that p times y prime is greater than equal to p times y for every y prime in the set py. So it's not only for one item, it's for all y prime in the py. So now we have to have that prices are greater than equal than zero. Because if imagine one entry is negative for some good, then we should have, given that all the entries here are greater than equal, and then you have that one price is negative, then you will have that the multiplication of this is less than py for some y, such that yl prime minus yl is sufficiently large. So you can blow up this entry of the vectors because there is a negative price there, that you can reverse the inequality. So now, this is not good, right? So we need prices to be greater than equal than zero, else they will lead to a contradiction. So that means that you have actually a positive price. So that means I don't need to pay firms to produce what I want. I just need to fix a price in the... So I don't need, sorry, to have a negative price, which would mean that they will pay me to produce something. I just can fix positive price, right? And positive price would mean they have to pay this positive price for inputs. Maybe they have some free inputs that I can give you as a government, so price zero. But outputs as well, they will sell it at a positive price. And then potentially if it's zero, they will give it for free. Okay? But according to this price, if they maximize profits, they will actually individually produce supplies such that added up will give me the original Y. Okay? So this is called the second welfare theorem, and this is an engineering problem because as the government, I want to implement an aggregate production plan, and I can do it not by forcing firms to do anything. I just can give them a coordination device, which is a price, and then I just let them maximize profits. And when they maximize profits, they will do what I want. So this is kind of a mechanism design kind of idea. Okay? So thank you. That's all for today.